Okay. Right. So I think we went over the most of the content of chapter 2.2 last time, and there were a couple of questions for homework. So let's go over that first. So the 2.2 homework for last time was 4, 7, 10, 11, 14, and 15. So we'll start with question number 4. Okay, so we start with a bit of a, I'd say tricky one. So for number 4, it gives us the graph of x cubed plus ax squared plus 2a minus 1x plus a plus 2. Plus a plus 2. So we have this graph, and it tells us that this graph passes a stationary point P regardless the value of a. The equation of the tangent line drawn from P is mx plus n. Okay, so the main point of this problem really, rather than the calculus aspect of it, I'm sure we're quite comfortable with finding the equations of tangent lines, is to find that point P that this graph seems to magically pass through no matter what the value of a is. Now, no matter, regardless of the value of a, that should give you a hint of how you should approach this problem to find that special point. If you see, there are a's kind of like scattered around in this equation here. There's one in the x squared term, there's one in the x term, and there's a constant term. So what I would like to think of is, if this point is going to be unaffected regardless of the value of a, then it must have some sort of special coordinate where it will make the influence of a turn into 0, right? So to see what I mean, let's group everything. So here we have it in the descending order in terms of x, but let's group all the terms we have of a. So let's group everything. Let's pull out a to the front, and then all the terms that have a, x squared, and then this is 2ax, right? 2, so that's 2x, and then here is plus 1, and then all the terms that don't have the a term, x cubed, and minus x plus 2 are the terms that don't have the a term. As soon as I write this, you will see that this polynomial is indeed a square, so x plus 1 squared plus x cubed minus x plus 2. Okay, now it becomes pretty clear, right? Our stationary point P, it must have the same x and y coordinate regardless of the value of a. And the thing that's attached to a is x plus 1 squared. If we make that 0, no matter how the value of a changes, the other term will always have that constant expression of x. That means that our point P needs to make this part, the x plus 1 squared, 0. So the x value, the x coordinate of point P would be negative 1. And if we plug in negative 1, this would be negative 1 plus 1 plus 2. So that would be negative 1.2. Okay? So if you see a polynomial with multiple, like here, we have x and a, it's maybe a good idea to say, hey, if the problem tells us that this value will stay constant no matter the value of a, we can group every term with a and then find that pattern that occurs there. So we got our point P, and all we need to do now is to find the tangent line from point P. Okay, so now it's everything as usual. Y prime, we should find it first. 3x squared plus 2ax plus 2a minus 1 would be our derivative, and our point of tangency is given, so we can plug in 1, so y prime of, negative 1 would be 3, and this would be minus 2a, and then plus 2a minus 1. So fortunately, our a's cancel out, so we don't need to deal with that. Okay, so that would be 2, and therefore our equation would be the line passing negative 1 comma 2 with a slope of 2. So that would be y equals 2 times x plus 1 plus 2, and that would be 2x plus 4. All right, so the value of m plus n would be 2 plus 4 equals 6, and that would be our final answer for number 4. All right, so kind of a cool problem there. Number 7. What is the area of the region surrounded by the tangent line on the curve? Ooh, there is a typo here. I don't know if I fixed that in our workbook. Oh, yes, I did. Okay, so the typo is fixed, so we don't have to worry about that. Not 5, this is 7. Okay, 7 asks us the tangent line at point 1 comma 3 on the curve y equals x cubed minus 2x squared plus 4, the x-axis and the y-axis. All right, so we first need to find the equation of the tangent line, and then we'll draw it out on the xy plane and try to get that area surrounded by those 3 lines. So first up, the tangent line. As usual, it's a pretty straightforward process. 3x squared minus 4x, and y prime of 1, which we're trying to find, is negative 1. So we get our equation. Our tangent line, I'll call it L, would have the equation y equals negative x minus 1 plus 3, which would be negative x plus 4. And if we draw that out on the xy plane, it would have a slope of negative 1 and have a y-axis, y-intercept of 4, and an x-intercept of 4. The area surrounded by our tangent line, L, and the x-axis and the y-axis would be this right triangle over here. So the area would be simply 4 times 4 times a half, which would be 8. So 8 would be our answer for this one. All right, so moving on to number, was it 11? Number 10? Okay. Ooh, so number 10 is a pretty interesting one. Now, if you solved number 10, you would have probably solved it algebraically, and that's perfectly a good, valid solution. I would have, if I had provided to you the shape of the graph, we might have gone in a little bit of a geometric direction, but we'll learn how to analyze these types of functions in our next chapter. So right now, learning how to do these things by algebra is equally important. But let's take a look at the 2 solutions that we have for number 10. Okay, so the problem itself is pretty simple. It asks us, okay, so we have the graph of y equals mx plus 2. So that's a line. And we have y equals negative x cubed plus 2x. Okay, and they intersect at 2 different points. And that's it. And we're asked to find the value of m. All right, so when we have 2 things that are intersecting each other, that means we got to put their equations to be equal to each other. So let's do that first. Negative x cubed plus 2x has to equal mx plus 2. And let's put everything on one side. I prefer a positive leading coefficient, so I'll put the x cubed, these terms on the right side. So x cubed plus we have m minus 2x plus 2 equals 0. And as you can see, it's a cubic equation. We learned how to solve cubic equations by factoring last time. We used a method called synthetic division. But in this case, you can see that this m minus 2 makes it pretty hard to determine a certain value of x that we can try. So we have to go back a chapter and remember that there was a unit in differentiation where knowing the fact that some polynomial equation had something squared in it told us that if we take whatever's in here and we set it to 0 and we plug that number back into the polynomial, then that polynomial will have let's say if this is x minus alpha squared, the polynomial will have p alpha equals 0 and p prime alpha equals 0, because if we take the derivative of this, it's going to be 2 times x minus alpha with the chain rule. So remembering that if something has a squared term in its quotient, and there's no remainder, here, I'll write it out in full for you. So if px equals x minus alpha squared times qx, and there's no remainder here, there could be, but assuming that it divides exactly, then p alpha will be 0, obviously, and if we take the derivative, p prime of x will be 2 times x minus alpha qx, and then by the product rule, we'll have a x minus alpha squared times q prime of x. But this term really doesn't matter, because if we plug in alpha, this will go to 0 anyway, and this will also go to 0 because it's a squared term. There's one more degree remaining. So we'll have these two equations to work with, and that should give you a strong background to attempt this problem, because it says we have only 2 different points. You might have learned in your algebra or pre-calculus classes that an equation with the highest degree x to the n plus blah, blah, blah. If the highest degree is n, then this equation equals 0 has at most n different real solutions. Okay, I think this is known as like the fundamental theorem of algebra, but we don't need to go that far. When we study parabolas, right? Parabolas start with x squared, so the most number of solutions it could have is 2. If the equation starts with x cubed, then it can be factored into at most, right? X minus alpha, x minus beta, x minus gamma, so some sort of 3 monic equations. That's a maximum. We can't have like a 4th equation, because that would make the highest degree 4. So here it's a special case because we have a cubic equation, but it tells us that we're only intersecting at 2 different points, which should tell you that this equation that we have here has to have a square multiple. So let's say x minus alpha squared, x minus beta, something like that. And we know that the highest order, the leading coefficient is 1, so the coefficient here is 1. But we should be able to sort of link that, right? Because we need a degree of 3, but we only have 2 different points where they intersect, so only 2 valid real solutions. Which means that we can do something here. We can plug in alpha into both sides and set that equal to 0. And then we can plug in alpha after we take the derivative. So let's start with that. So let's plug in alpha. So alpha cubed plus m minus 2 alpha plus 2 equals, and this entire side goes to 0. Okay, so now we've done that. Let's take the derivative of this polynomial. 3x squared plus m minus 2x plus 2. Now I'll get rid of this 0 for now because it's sort of confusing us. And remember, our goal is to set this equation and to verify that it has only 2 different points. So that's why we set it up like that, okay? Equals, let's use the product rule, 2 times x minus alpha, and then x minus beta stays the same, plus x minus alpha squared stays the same, and then the derivative of this guy is just 1. And then we plug in x equals alpha again. That means that this will go to 0, and this will also go to 0. So 3 alpha squared plus m minus 2 alpha plus 2 equals 0. Okay, so we got that going for us. What we can do here is now try to solve this system of equations. Right, so what we can do is So we got that going for us. Okay. Let's try this. You see, we have m minus 2 alpha plus 2. We have n minus 2 alpha plus 2. So maybe we can simplify this into a simpler equation. We can move 3 alpha squared onto the other side and say, hey, m minus 2 times alpha plus 2 equals negative 3 alpha squared. And then we can plug this in place of this and get a much more simpler equation. So we get alpha cubed minus 3 alpha squared equals 0. And we can factor alpha squared, alpha minus 3 equals 0. So we get alpha equals 0 or alpha equals 3. Okay, so we got some possible values for alpha. Right, cool. So now we need to determine if this is correct or if that is correct. All right, let's take a look. If alpha is 0, then what will happen to beta, right? So if alpha equals 0, we can plug alpha back in here, right? We can plug alpha back in here and let's see. If alpha equals 0, we plug in x equals 0. That will give us 2 equals 0, right? Because this is going to be 0, this is going to be 0, and this only the 2 will remain. And since alpha equals 0, plugging in alpha will cancel out this entire term, leaving us with the equation 2 equals 0, which would be a contradiction. So alpha equals 0 won't work in our case. So the only available option is alpha equals 3. If we plug in 3, we'll get 27 plus 3 times m minus 2 plus 2 equals 0. And now we get a valid equation that we can solve for m. Cool. Okay, so 3m equals, we got 27 minus 6, right? Plus 2. Is that right? (27 times 3m minus 2 plus 2). Okay, so we got this guy over here. Oh, so alpha cubed. squared. Oh, did I not take the derivative here? Oh yeah, oh yeah. What am I doing? Okay, so that solves our mystery. Yeah, okay, so the derivative here is 3x squared plus m minus 2, and that's it, right? So when we plug in alpha, it should be, okay, let's go over this again. Okay, so 3 alpha squared plus m minus 2 should be equal to 0 on all sides. Okay, so we should get m minus 2 equals negative 3 alpha squared. And then we can substitute m minus 2 back in here. So we'll only substitute this part. So that means alpha cubed plus minus 3 alpha squared, alpha plus 2 equals 0. That means that we have 1 alpha cubed and minus 3 alpha cubed, negative 2 alpha cubed plus 2 equals 0. So alpha cubed should be 1. So there's only one possible value of alpha. Alpha equals 1. Okay, so now we got it. So now we can plug this back into the original function here and set that equal to 0. So 1 plus m minus 2 plus 2 equals 0. So m equals minus 1 would be your answer. Okay, as long as you didn't get confused about the derivative, then the process should have been not too difficult. All right, so that's how you solve it algebraically. As you can see, you put these two together and then you set that equal to something squared times something else. And then you set up a system of equations, solve for alpha, and then find m. Right, so that's a little bit of, I guess, some algebraic work, but it isn't what I would call, the quickest or like the easiest solution for this problem. What I want to show you is how the graph actually looks like for this function. Okay. The graph of this function actually looks like this. So we can actually make some predictions about what this graph will look like. It's negative x cubed plus 2x, which means we can factor out an x. Do I want to leave the negative? Okay, I'll not leave the negative out, and then I'll have negative x squared plus 2. So we can actually find all our solutions here, right? So the solutions are 0 and then plus and minus square root of 2. So we'll have 0 and plus square root of 2 and minus square root of 2 as our points of intersection of this graph. If we send this to negative infinity, the negative x cubed term will always win over the x term because it has a higher power, which means that as we go to negative infinity, it should decrease very steeply. Increase, because we have a negative sign in front of the x cubed term, then it should be a very large positive number. So we start from a very high positive number, and then as we go to positive infinity, we should get a very small negative number. So in this process, it has to start from a very high number, decrease, pass through these points, and then go down to negative infinity, essentially. So this is what our graph will look like. It will sort of look like this. Of course, we're only making predictions now. In the next chapter, we'll formally learn how to deal with these things. And our line is a line with slope m, so that's an arbitrary number. But we also know that the y-intercept will always be 2. So 2 is like on the positive side here, so sort of like that. So from our algebraic solution, we know that, I'll just write it over here quickly again. So alpha cubed equals 1, alpha equals 1. 1 plus m minus 2 plus 2 equals 0, so m equals negative 1. So we know by algebra that the slope is going to be negative 1, so the y-intercept should actually be close to here. So, okay, the point is that if you know how these graphs are drawn, then we can make some quicker conclusions about how this problem could be solved. Okay, by that I mean, we have a line that goes through 0, 2. So it could be any line with any slope, but it has to meet with this curve exactly 2 times. Now, most lines will intersect this curve 3 times, or maybe if we go steep enough, we'll intersect the curve 1 time. But there's only one instance that we can geometrically verify, and it's this particular line here. Let me see if I have a blue marker. It's this line over here, where it's perfectly tangent at this point, and it intersects the curve again at this point. Okay. We also can geometrically see that any line that's steeper than this will never get tangent at the bottom portion here. So if we get a positive steep slope, it will intersect the curve once here, but there's really no chance for it to get exactly tangent at some specific point. Again, we'll learn more about the geometry itself in the next chapter, but this is just a preview of what you can do by visually analyzing these functions. Okay, so now we know that the only situation that we actually need is this tangent line here. So let's say that this tangent point is t, and what we can do is we can find a specific tangent line that goes through an external point, which is 0, 2. So we'll get y prime. So this is an alternate solution. Y prime equals negative 3x squared plus 2. And here, plugging in t, negative 3t squared plus 2. And then x minus t. Plus f of t, which is going to be negative t cubed, negative t cubed plus 2t. So that's going to be our equation of the tangent line, and that tangent line has to pass through 0, 2. So now we'll plug in x equals 0 and y equals 2. 2 has to equal negative 3t squared plus 2 times negative t minus t cubed plus 2t. That means that, what can we simplify here? Negative 2t and positive 2t can cancel out, which means that 4, so we have 3t cubed and minus t cubed, so that's 2. 2t cubed equals 2, right? So we have positive 3 and minus 1. So t has to equal 1. And if we plug t equals 1 back in here, we'll get the slope of negative 3 plus 2 equals negative 1 right away. Okay, so that might be simpler. That is simpler, right? Because here we have to realize the fact that this can factor into something squared times something. We have to set that up. We have to plug in that specific double root, take the derivative, plug it in again, get a system of equations, plug it back in, substitute, solve for alpha, and then solve for m. But here, if we just realize that the situation that the problem is talking about is just a tangent line to the curve, then all we need to do is really solve a relatively simple problem of finding a tangent line on the curve that goes through an external point, right? And as you can see, there's only one solution here, so that does verify our geometric visual analysis that you can't get a tangent line down here. So these are 2 ways to solve a problem. By the time you're done with this unit, you'll be very, very comfortable with solving it this way. But for homework, I sort of think that you might have more gone down this route. So both, I think, are good perspectives to have. But usually noticing these visual features help you get to the correct answer faster. Yeah, so that was number 10, and the answer is negative 1. All right, so the next problem would be number 11. So number 11, compared to number 10, I think it's pretty relatively simple to do. It asks us, what is the line with the maximum possible slope? So we're trying to find the maximum value of the derivative. So the function that we're talking about is a third degree polynomial, negative 2 over 3 x cubed minus 2x plus x, 2x cubed, 2x squared plus x plus 1/3. And that's the graph that we're trying to analyze. The line with the maximum slope is ax plus b. Okay, so let's set this as y, and then we'll compute y prime. So that's going to be 3 going down, negative 2x squared minus 4x plus 1. And we're basically trying to find the maximum possible value of this, which is pretty easy because it turns out it's a quadratic, right? So remember, when analyzing quadratics, the most important features are its axis of symmetry, because when you find the vertex will be on the axis of symmetry, and the vertex is the key to finding like the global maximum and the minimum of a function. So the maximum value of this function, it's going to be a parabola that is concave down. So our axis of symmetry would be negative b over 2a. So it would be 4 over negative 4, which would be negative 1. And if we plug in negative 1, it would be negative 2 plus 4 plus 1, so that would be 3. So our maximum derivative would be 3, so that automatically gets us y equals 3x. And then our x value would be negative 1, so we need to plug in negative 1 to find our function value. So that would be plus 3 over 2 minus 2 minus 1 plus 1 over 3. So that would be minus 2. Right, it would be minus 2. So we can plug in our function value here. So our graph will, this equation of the tangent line would be 3x, and then it's going to be plus 1, and the value of a plus b would be 4. Okay. So always don't forget about how important quadratic functions are. You'll see them appear quite a lot, even in higher level math, and it's important to quickly be able to find the maximum and the minimum of these quadratic functions. Okay, the next question is number 14. The tangent lines of the curves y equals x cubed plus ax and y equals bx squared plus x plus 4. They equal each other at x equals 1. So this is the case where we have two curves sharing a common tangent line, and that would mean that the curves are tangent to each other. Okay, so if you recall from last lesson, the only two things that we need to do is make sure their function values are the same and their derivatives at the point are the same. And this is pretty easy to verify since we're given x equals 1. So the first equation we'll have is we plug 1 into each of these. So 1 plus a equals b plus 1 plus 4, so that's b plus 5. And that would be our first equation. Our next equation would be taking the derivatives of each. So this would be 3x squared plus a, and this would be 2bx plus 1. And plug in x equals 1 into both of them. 3 plus a equals 2b plus 1. And that's it. We just need to solve this system of equations. What I could do is I could set both of these equal to a. So a equals b plus 4 in this case, and in the bottom, a equals 2b minus 2. So we can now solve for b. B equals 6 and a equals 10. And there you go. Find the value of a times b. So the answer would be 60. Okay, yeah, so that's how you would solve curves that are tangent to each other. And the final question that we have is number 15. All right, so number 15 tells us the tangent line at point -1, 3 on the curve y equals 2x squared plus 1 is also tangent to the curve y equals 2x cubed minus ax plus 3. Find the value of a. Okay, so it's easy enough, I think, to find the tangent line to y equals 2x squared plus 1. So at point 1, 3, right? So we can do y prime equals 4x and set up the equation y equals 4 times x minus 1 plus 3 equals 4x minus 1. Okay, so we got our equation, 4x minus 1, and 4x minus 1 must also be tangent to the curve 2x cubed minus ax plus 3. So what we can do here is we can treat it as the same thing as number 14 because we have two curves. Well, technically the second one is a line, but no matter, two graphs are being tangent to each other, which means that they have to share the same function value and they have to share the same derivative. In this case, the derivative is 4. So that will, in my opinion, that will be a little bit quicker rather than trying to set up a whole new tangent line in terms of t and then solving a system of like a and t and x, right? So our second curve is 2x cubed minus ax plus 3. So let's set up our equations here. Number 1, although, yeah, we are going to have to solve an equation about a and t. So let's set the tangent point as x equals t, okay? So number 1, the function values must equal each other. 2t cubed minus at plus 3 equals 4t minus 1. And number 2, their derivative. So the derivative of this guy is what? 6x squared minus a, right? 6t squared minus a must equal 4. So now we have to solve this system of equations. I can see that it's easier to substitute, it's easier to represent a in terms of t, so we'll go ahead and do that. A equals 6t squared minus 4. And then we can plug this back into the original equation. 2t cubed minus, so we have 6t squared minus 4 times t plus 3 equals 4t minus 1. And all we have to do is rearrange it, right? So we have 2t cubed minus 6. Maybe I do prefer solving equations with positive leading coefficients, so maybe we'll move everything over to this side. So we have 6 minus 2, so that's 4t cubed. And where's our t squared? Do we have a t squared term? I don't think we have a t squared term. Okay, so we have, if on this side we have like 4t and then this is 4t, so that will get canceled out. So we have 4t cubed, and then we'll move this over to that side. Minus 4 has to equal 0. So t cubed has to equal 1, t has to equal 1. So there's only one option here. And what is that we're trying to find? Find a. So we can plug this directly in. So a equals 6t squared minus 4. So that's 6 minus 4 equals 2. And there you have it. We didn't need to use synthetic division or anything. The numbers work out pretty nicely in this case. All right, so a equals 2. And that's all our problems for the workbook so far. And today we'll follow up on the final contents for this chapter, which is the mean value theorem and Rolle's theorem. Okay, so as I said last time, this is one of the more important theorems that you will have to memorize, and will come up a lot in probably Rolle's theorem and mean value theorems. You'll probably see mostly in written questions where you have to prove something, but it can also be pretty sneaky in some ways, and you might have to use them in some special contexts. It's not that commonly used in mainstream, some of the more common problems that you'll solve, but it's definitely something that you should know and be aware of. Okay, so let's start with Rolle's theorem, because that's a little bit more of a simple case. So this is how you spell it. Okay. So basically, if you take a look at your notes, it will say this. If function f is continuous on the closed interval ab, differentiable on the open interval ab, and fa equals fb. So let's try to draw that out and see what that means. So number one, it has to be continuous on the closed interval. And number two, it has to be differentiable on the open interval. And number three, in this case, f of a equals f of b. Okay, so let's say I have x equals a here, and it has to be on the same function value, so the y coordinate will be the same. So this is x equals a and x equals b. Now I can draw whatever function I want as long as it's differentiable. So maybe I'll do something like that, okay? So this is just like any function that satisfies this. And what Rolle's theorem tells you is that there exists at least one c between a and b so that f prime c equals 0. Okay, there exists at least one c as a constant, and that has to be between a and b. So we can put it like that. C is in the interval a comma b, between a and b, so that f prime of c equals 0. And as you can see on my drawing here, we can see actually a couple of points where the derivative is 0, like here, here, and here. The important part is at least one exists, right? So in a different curve, I might not have as many ups and downs, but no matter how your curve is drawn, even if I draw my curve like this, we can see that there's at least one value where the derivative equals 0. Okay. The proof is intended to be visual for our high school purposes, is to check visually, right? So this is the simplest type of curve that you can have. Either it curves upwards, curves downward, or is flat, in which case, a constant flat function will always have a derivative of 0. So even if it curves slightly upwards or slightly downwards, we can visually see that it has a peak point and that it goes down. So that's why it would have a derivative of 0. Again, analyzing what does going up actually mean and what does going down actually mean, we'll cover all of that into the next in the next chapter. All right, so that's Rolle's theorem. And the second theorem that we need to remember is sort of like a generalization of this theorem called the mean value theorem. Okay, so the mean value theorem, it's often abbreviated as MVT, just like, IVT, the intermediate value theorem that we covered in, was it limits, I think? or continuity. Yeah, it was one of those. Okay, so the mean value theorem is a generalization of Rolle's theorem, and it says that, hey, A comma B, the first two conditions are the same, right? It's continuous on the closed interval and differentiable on the open interval. So this carries over into the mean value theorem. But the third condition is now gone. So now there's really no need for f of A to be equal to f of B. So I can say that, hey, A can be over here and B can be like up here. And what the mean value theorem says, there exists at least one C, which is between A and B. So we can say, hey, it's in the open interval A and B, so that f prime of C equals the average rate of change between A and B. So that's B minus A under f of B minus f of A. Okay, so Rolle's theorem is really just a specific case of the mean value theorem where this average rate of change would be 0, right? Because the function value is the same, so they would have an average rate of change of 0. But in this case, the average rate of change would be the slope of the line that connects the 2 points together. And no matter what curve I draw, whether it's this curve that goes like that, or a very, shallow curve that goes like this, there will always be at least one place where the slope of the tangent line equals that of the slope of the secant line, or the average rate of change between A and B. So you would have this line and this line in the blue curve, and you would have this line in the black curve. As you can see, they are all parallel to the average rate of change, and the slopes are the same. Okay, so that's what these theorems are. When you memorize these, just remember to know the conditions for this theorem to be held true and what this says about the function. And they both tell you that there has to be something somewhere in the curve. It doesn't show us where in the curve, but somewhere there has to be a point where the tangent line equals the average rate of change between these 2 points. And Rolle's theorem is just a special case where the average rate of change is 0. Yeah. So there are a couple of problems involving that in the workbook. So let's get started with that. Okay, number 16 through 18 will cover some potential problems that you might see on these theorems. Okay, so let's start with number 16. For a function f of x equals negative x squared plus 2x plus 4, what is the value of constant c on the interval 0, 2? So we're given the closed interval 0, 2, and we're trying to find the constant c that satisfies Rolle's theorem. So if you don't know what Rolle's theorem is, you wouldn't be able to solve this problem, right? Okay, so the Rolle's, we first have to check the conditions, right? Is this continuous and differentiable? Yes, all polynomial functions, as you recall, are continuous and differentiable everywhere. So that's good. And all we need to do now, and that is to find that value of c. So because they're continuous and differentiable everywhere, the Rolle's theorem guarantees you that there will be a value of c in this interval. So that, we need to check one more thing, right? Rolle's theorem only works if the left hand and right hand function values are the same. So that's what we need to check for first. If we plug in f equals 0, x equals 0, we'll get 4. And if we plug in x equals 2, we'll get negative 4 plus 4 plus 4, which is 4. So now we can also check that f of a equals f of b, right? So we got all our 3 conditions down, which means that there will exist a value of c. But we're trying to find that value of c, so we're going to set f prime of c equals 0. So f prime of x would be negative 2x plus 2. So that will become negative 2c plus 2 equals 0. So c equals 1. And that would be our answer there. Okay, so this is a very common type of problem asking you to actually find the point where the derivative equals 0. All right, 17. The graph of polynomial function x is shown below. So let's try to draw that one. So we have this going on, and it's a curve that dips down here and goes up, and then down and up, sort of like that, right? And then we have the y-intercept being marked, and then this is going to be A, and that is going to be B, and where is C? There's a line that goes through here. Okay, so it starts here, it goes through here, and then C is right here. Okay, so that's our curve. There are p distinct real numbers x that satisfies Rolle's theorem on the open interval AB. So we're looking at from here to here. And q distinct real numbers that satisfy the mean value theorem on open interval AC. Now, it's a polynomial function, so we're guaranteed that the function will be differentiable and continuous, so we can satisfy conditions 1 and 2. So let's look at the Rolle's theorem example first, right? It's on a closed interval. It's on the open interval AB. So they have the same function value as the y-intercept as it is shown. And we can visually verify that the zero derivative occurs here and here and nowhere else within this closed interval. So the value of p would be 2. And the mean value theorem on A and C. So as you can see, this is the average rate of change we're looking at, and on the interval from A to C. So we can see that we have a parallel line here. We can find one here. We can also find one here, sort of like that. And we can also find one at the top. So we have 3 instances where the mean value theorem would be satisfied. So we have q equals 3. So p plus q would have a value of 5. Okay, so I think these are pretty easy questions compared to like some of the ones we were doing before. And what I want to share with you is actually number 18. So if you can just, if you can pause the video, I don't think anyone's watching live right now. So if you can pause the video and just think about how to solve number 18, because it's a limit problem. Initially it has nothing, it seems to have nothing to do with like what we were just doing now with these two. But it's quite a special limit problem. So pause for a bit and think about how you might solve this. And we'll go over the solutions right now. Okay, so number 18, the problem states that differentiable function f of x satisfies, and we're given quite a unusual limit x goes to infinity of f prime of x is given to us, and the value is 2. And it says, hey, find the value of limit x goes to infinity of f of x plus 2 minus f of x minus 1. X minus 1. And that's it. This is all we're given. And function f is differentiable. Okay. If we try to plug this in, f of infinity minus f of infinity. And since the limit of f prime is 2, so you might start to picture what's an example of a function that will have a limiting derivative of 2. So if this dotted line is like a line of slope 2, maybe f of x will look something like that, where the derivative gets really, really close to, 2 as you go to infinity. So it's probably increasing. So you would be dealing with an infinity minus infinity limit. But there's nothing much else you can do unless you gather more information about f of x, which there seems to be none of, right? So that initial visual thought is good, but we need to sort of algebraically manipulate this limit first. We're quite familiar with seeing like these types of things, but with denominators in them, right? So if we put a denominator in, we'll be able to represent this as like, some average rate of change, I think. So if we've been looking at this for quite a bit, right? We've solved quite a few problems on this. The input here is x plus 2, and the input here is x minus 1. So there should be, in the denominator, if we made one artificially, it would be x plus 2 minus x minus 1. So it would have a denominator of 3. So why don't we transform our limit like that so we can get at least something out of it, right? Divide this by 3. And then since we divide it, we have to multiply, and that can go outside our limit. Okay, so this represents what? The average rate of change from x minus 1 to x plus 2, right? So we have x minus 1 to x plus 2. Okay. Remember that we are told that the function is differentiable. Now, this is why when you're reading a problem like this, you want to pay attention to every detail that they give you, because even small details like this can be very important in solving this problem. We see that the average rate of change from x minus 1 to x plus 2 can be given with this expression, right? And we know that the function is differentiable, which means that differentiability implies that it's also going to be continuous everywhere. So we can say by the mean value theorem, we can say that there exists C, which is between x minus 1 and x plus 2, so that f prime of C equals this, f of x plus 2 minus f of x minus 1 over 3. Okay, so now this is big because C is always bounded between x minus 1 and x plus 2. So when x goes to infinity, C has to move with that interval, because by the mean value theorem, it guarantees that for any interval for x minus 1, x plus 2, there will exist some value so that the derivative is equal to this. Okay, so now let's turn the limit of x into a limit of C. Remember that the 3 is still there, so let's pull 3 out to the front. Limit x, not x, but C goes to infinity, right? Because as x goes to infinity, C has to stay within these two numbers, so C will also go to infinity. Now this expression is equal to f prime of C. And as you can see, just like that, we have exactly what we need, right? Just this one has x as its variable, and this one has C as its variable, so the limit value will be exactly the same. So we can just plug in 2 and get 3 times 2 equals 6 as our answer for this problem. Okay, so initially this seemed to have nothing to do with the mean value theorem, but we actually had to apply that to guarantee a fact that we had to use in our final calculation. So once again, algebraic manipulation is important, but also applying the mean value theorem when it's needed, right? And in most problems, it won't be that much of a use because it can't pinpoint the exact value that you want. You would actually have to go through real calculations to pinpoint that value. But in this case, just knowing that there exists a point is enough to get to the answer of the problem because it's a limit. So I think this is a pretty difficult problem if you just saw it on a calculus test without the context that we placed it in right now. But it's our job to notice these things and think about what we can throw at it and what gives us the evidence to throw at it, right? Because we're given that it's differentiable, and we have to wonder if this is a pretty is this an important thing that they gave us, or is it not so important as some of the other problems are? But in this case, the fact that it is differentiable allows us to use the NVT. All right, so that is the end of chapter 2.2. Now, a lot of things that I said today, I said that we would get into more detail in the next unit. So the next unit is probably going to be the biggest and, in my opinion, the most important out of all the chapters in Unit 2. So the next chapter, 2.3, is where we'll really combine everything that we learned about limits, continuity, tangent lines, polynomial factoring, all of that into analyzing the graphs of cubic and quartic functions. You saw a lot of cubic functions today, and tomorrow, next time, we'll get really a visual approach with how we deal with those types of functions. Okay, so no homework today, so take a time to review all the concepts that we've gone through so far, and I'll see you in the next chapter. All right, goodbye.